Welcome to the Discrete Universe podcast. Today we're diving deep into how quantum geometry dynamics, or QGD, offers a really unique perspective on some major observations recently. We're talking about the signals picked up by the LIGO-Virgo observatories.
Yes, the ones usually interpreted as gravitational
It's
waves.
exactly cornerstone of Einstein's general relativity, right?
Yeah.
But QGD comes along with a fundamentally different explanation.
It does. It's rooted in QGD's core ideas about space, matter, and, how they interact.
So our mission today is to unpack QGD's take on these signals. We want to explore the why behind it and really pinpoint how it differs from the standard gravitational wave story.
And we'll be drawing on QGD's basic principles, its ideas about gravity, this thing called the preonic field, and its view on cosmology, too.
Okay, let's unpack this. Because the idea that what we think are gravitational waves straight out of Einstein might be something else entirely, that's a big claim for physics.
It is a big claim, and QGD gives a specific theoretical basis for it. Fundamentally, QGD actually precludes the existence of gravitational waves as described in general relativity.
Whoa, okay, precludes them entirely. So what are the LIGO-Virgo signals then, according to QGD?
It interprets them as preonic waves.
Preonic waves. Okay, that's probably a new term for many listening, even those familiar with the standard model.
All right, good.
What exactly are these preonic waves in QGD?
Right. So think of them as variations, like ripples, but not in space-time. They're variations in the polarization of what QGD calls the fundamental preonic field.
The preonic field?
Yes, it's a foundational concept in QGD. This field is made of fundamental particles called preons, plus, and these waves, these fluctuations in the field's polarization state, they travel at the speed of light, c.
Okay, propagating at c. But what's really interesting is you mentioned QGD predicts these waves could do something else.
Yes, that they could actually impart momentum to the detectors. That's a key potential difference.
So just to be clear, instead of space-time itself rippling, QGD is saying these huge cosmic smash-ups are shaking up a fundamental field of preons.
That's the core idea. And QGD connects these disturbances directly to things like merging neutron stars or black holes, these binary systems. As they spiral in and accelerate, QGD says they cause intense polarization of this preonic field around them.
Okay, now this is where it gets really interesting. These mergers that LIGO and Virgo see, these incredibly violent events, QGD says they're stirring up this preonic field in a major way.
Precisely. And QGD suggests the signals we detect are likely these intense magnetic fields, which are essentially polarized preonic fields. And the signal shape is modulated by the binary's orbital dance.
So the field acts like a magnetic field.
Yes, the theory proposes that the magnetic field generated by this preonic polarization during the merger could effectively, it could mimic the predicted gravitational waves.
Mimic them so closely that we can't tell the difference with what we have now.
That's a crucial point QGD raises. It suggests the effect on the LIGO-Virgo detectors, the tiny length changes, could look almost identical, whether it's a gravitational wave from GR or these intense, fluctuating magnetic-like fields from QGD's perspective. They might be undistinguishable with current methods.
That's quite a challenge to the standard interpretation. It makes you ask, well, what about gravity itself in QGD? How is it different from GR?
Ah, yes, gravity. That's another major departure. In QGD, gravity is proposed to act instantaneously.
Instantaneously, not limited by the speed of light.
Correct. That's a stark contrast to theories like GR, where gravity propagates, as waves at speed c. Furthermore, the QGD equation for gravity, it predicts both attraction and repulsion, depending on distance.
Attraction like we normally see, but repulsion at very large distances.
Exactly. QGD proposes that beyond a certain very large scale, gravity flips to become repulsive. And it links this repulsion to what cosmologists currently call dark energy. So it's suggesting a completely different mechanism for the universe's accelerating expansion.
Wow, okay. Instantaneous action and repulsion at large scales? Very different. So if both GR and QGD might explain the LIGO signals, how do we possibly figure out which one is right?
Yeah, that's the million-dollar question, isn't it? QGD proponents acknowledge this. They state that a testable prediction unique to QGD is necessary.
A unique test.
Right. And one possibility goes back to those preonic waves. If the signal is these polarized preons, plus, remember how I mentioned QGD predicts they'd transfer momentum?
The momentum transfer, right. How would that actually show up in an experiment? Could we see it?
Well, the idea is that these preonic waves interacting with the detector mirrors or maybe other parts, might cause tiny effects besides just changing the arm lengths.
Yeah.
Maybe minuscule pushes, tiny changes in the momentum of the test masses themselves. It's subtle.
So not just measuring distance changes, but looking for a tiny kick?
Sort of, yes.
Yeah.
Designing experiments sensitive enough to detect such a secondary effect, if it exists, could be a way to differentiate. It's about the nature of the interaction.
Fascinating. It really underscores that it's not just that we detect something, but precisely how it interacts with our instruments. Now, you've mentioned this preonic field polarization a few times. How does QGD connect this to, say, electromagnetism?
Good question. QGD actually proposes that electromagnetism itself arises from the polarization of the preonic field by charged particles.
So particles polarize this field.
Exactly. And in this view, what we call a magnetic field is essentially a region of polarized preons plus.
Ah, okay. So those intense fields from merging binaries we talked about, they're just highly polarized regions of this fundamental preonic field.
That's the interpretation within QGD, yes.
Yeah.
It provides a unified picture.
And does this extend to QGD's view of black holes? Are they singularities like in GR?
No, QGD's description is different. It views black holes as extremely dense objects, but not point singularities.
Yeah.
And importantly, it suggests they generate extremely intense polarized preon plus fields, particularly along their magnetic axis.
Which means if two of these QGD black holes or neutron stars merge,
It would cause massive fluctuations and reconfigurations in this already intense polarized preonic field. A huge disturbance.
and those disturbances propagating outwards are the preonic waves detected by LIGO?
That's the proposed mechanism, yes.
Yeah.
It ties the observation back to the fundamental constituents and fields posited by QGD.
This whole framework, it really feels like it's reaching for something deeper, a more fundamental layer beneath the standard model in GR. Which brings us to Hilbert's sixth problem. I saw that mentioned. How does it connect?
Ah, yes, Hilbert's sixth problem. David Hilbert, the great mathematician back in 1900, challenged physicists to axiomatize physics, put it on a rigorous logical foundation like mathematics.
To build physics from the ground up on clear axioms.
Precisely. And
Ah.
the fact that we still have general relativity for the large scale and quantum field theory for the small scale, and they don't, play nicely together, that shows Hilbert's challenge is still very relevant. We lack that single, consistent, axiomatic foundation.
So QGD sees itself as an attempt to actually do that, to build that foundation.
Exactly. It's an attempt to address Hilbert's challenge by proposing a new set of axioms, things like strict causality, discrete space, and building physics up from there, aiming for a unified description.
So it's not just about explaining LIGO signals differently. It's part of a much bigger picture, trying to rewrite the foundations.
It's a good way to put it.
Yeah.
The LIGO interpretation is a consequence of this broader framework that also tries to tackle gravity, unification, dark energy, all from these first principles.
Okay, so to sum up QGD's view, those incredible signals from LIGO-Virgo, maybe not space-time ripples after all, but rather intense, fluctuating magnetic-like fields, these polarized preonic fields churned up by merging giants.
That's the core alternative.
Yeah.
And it all stems from QGD's very different picture of gravity instantaneous, mediated by discrete space structure and the role of these fundamental preons.
And the big challenge, the next step, is finding that unique test, that specific prediction QGD makes that GR doesn't, to see if we can distinguish them experimentally.
That's absolutely crucial for the theory to gain wider acceptance.
This deep dive into QGD's perspective certainly opens up some profound questions about gravity, about what the universe is fundamentally made of, and about how we interpret the messages the cosmos sends us. We definitely encourage you, the listener, to keep exploring these ideas in quantum geometry dynamics. Consider how this framework might reshape our cosmic view. Thank you for joining us on the Discrete Universe podcast, and here's a final thought for you to chew on. If gravity really is instantaneous, as QGD proposes, how might that fundamentally change our understanding of cosmology, the evolution of the entire universe on the grandest scales? It's definitely something to think about.